Okay, microphone works. Welcome back, everyone. We're starting on time. The first two plenaries, we kind of looked at high-level information about floating wind projects with OEM, developer, grid operator perspectives, and now I think we're ready to dive further into some of the technology and commercial details over the next three plenaries. The first one of those three having a more electrifying flavor. So before I invite Maxime Toulout, chair of this plenary, to the stage, I will read his short bio. Maxime Toulout is working as Markets and New Solutions Director for the Power Transmission Business Group in Nexans. Nexans connects offshore wind farms to the grid with high-voltage cables. Maxime has 15 years of experience in HV subsea cable projects, the majority for offshore wind, combining technical expertise with commercial and strategic experience. His responsibility is to engage at early stage on innovative projects such as floating offshore wind, great, to get a precise understanding of innovations and developments required. Maxime holds an MSc in electrical engineering. So, without further ado, Maxime, please come to the stage and let's get started.
Thank you very much, Louise. Hello, everybody. Good afternoon, and welcome to the session called Delivering Floating Electricity. So I hope you enjoyed your lunch, got some coffee, and are energized for this afternoon for the good program that we have. So this morning we heard about public policies and as well in the various countries, and as well the latest updates from the developers and from RT in France. And now I'm very happy to see that the connections of floating wind to the grid has made its way very early in the program, showing the criticality of having reliable and innovative grid connections for offshore wind and especially for floating wind. So I would like to thank FOWT organizers to give me the opportunity to lead the three speakers, very enthusiastic and experienced speakers that we'll have today on stage. First of all, Anna can come on stage from Ocean Winds. She will discuss the floating wind project's connections to the grid from a developer point of view. And then she will give us some insights of the lesson learned and challenge that they have from the pilot and pre-commercial project that they have done, and how this will apply to future commercial projects. Anna, please join me. Then we'll have Alfredo from Hitachi Energy. He will share what they are doing in terms of R&D and innovation, and what experience can be transferred from bottom fixed converter and substation to the floating wind business. And last one, Michael from Technip FMC will then share with us the challenges associated to dynamic cables and also the contrasts and the lesson learned that we have from the oil and gas sector. So we'll have the three presentations in a row, and then we'll have, hopefully, I'm sure they will keep the time, we'll have some Q&A at the end with everybody. So first, let's start with Anna. Anna has more than a decade of experience in offshore wind. She started her career at Scottish Power, working as lead contract manager and lead electrical engineer on offshore wind projects, and then she moved to Ocean Winds, where she led the electrical department. She's now serving as electrical engineer associate director at Ocean Winds, where she plays a key role in supporting the technical director in electrical and general technical matters. Anna, the mic is yours.
Thank you everyone. Thank you, Maxine. I'm glad to be here with all of you, and in particular to speak about my day-to-day and my passion, offshore floating wind. So I try to, we have the delivery floating electricity at the topic, but I try to focus more on, are we ready to go for commercial scales or not? So from the experience that Ocean Wind has, they started long time ago. They started with a prototype that they installed with a 2-megawatt turbine in 2011. That was a long time ago, where they have that prototype on the sea for 5 years. After that, with no yet commercial, that was starting with the WindFloat Atlantic 1. That was 1 turbine at the beginning, and then they decided to go to a small-scale commercial. Ocean Winds decided to have 3 turbines. That was 25 megawatt, that they are actually in operation for 5 years. And we are in the current construction. Hopefully we finish by end of the year with EFGL here in France, with also 3 turbines. The objective to that is to learn, and we will focus then later in the next slides, was to learn and try to get as much information as we can to see if we are ready as developer, as supply chains, as the market, to go to a bigger commercial scale. And then what the Ocean Wind has in the pipeline is next project, next development. And for that, we really need to be all ready. We really need to be commercially ready, and we need to go for bigger scale projects. So we have projects in South Korea, we have projects here now, in France, we have also in UK, and of course we have also in US in the California coast. So at the end for Ocean Winds is key offshore floating wind. We have 1/3 of our pipeline is offshore floating. So we are really pushing for this go ahead. What can I say about our project that is already under operation, WindFloat Atlantic? We are going to be now in May for 5 years in operation. We have been learning a lot. We learn a lot in how to integrate the different parties, different stakeholders, including turbine suppliers, authorities, ports, fishermen. So everyone, that was a key lesson learned for us to implement in the following project that was and is under construction, EFGL. What is other particular thing that we have in EFGL? EFGL is installed in a very protective area. So we need to understand the environment. We have been studying a lot the biodiversity that is there, and we are going to be the first project to be very friendly with the environment in terms of understanding what is happening there. For that, we are including some innovative ideas. One of them is to have biohubs in the floaters. The project, as I said before, was a bigger scale in terms of wind turbine comparing with the previous one, with the WindFloat. That one was 10 megawatt turbine, or is 10 megawatt turbine, and will be installed now, and finally will be in operation by end of the year. So what we have learned from all of this? What we can get from that? So we have learned OW has gained a lot of experience. One of them is we have gained to prove that the wind turbine, the technologies works, that they are suitable for those projects. Second, understanding also the key interfaces. And when I say that, is the behavior of the different elements of the project. That means floater with turbine, floater with cables, cables with mooring, mooring with floater, and so on. There are so many interfaces that thanks to this experience, this small-scale project, we have earned this understanding, to better understanding the interfaces. Also, another lessons learned is about the lead time and the engineering time scales. Why I say that? Because the maturity of these elements is not the same than in bottom fixed. And that is the reality, and we need to be aware of it. The engineering takes longer, takes time, and we need to take into account that in the construction of the project. So for that is the next also lessons learned. Design, construction, and installation timeline, and also, of course, different lessons learned then. And the most important thing, or one of the most important things for us also, is we have a track record of 5 years of operation and maintenance that we are now implemented in EFGL, and we are going to implement in the next project. So what are the challenges that we see as the commercial scale? The challenge is the technology readiness. That means the state of art of the wind turbine. We need the wind turbine suppliers who work together with us to do the research and development, and then to achieve to have the turbine ready for a bigger scale. The same together with the floater designer, because at the end they need to work on the same direction. Also, supply chain in general and industrialization. That means that we need to work together, a collaborative approach. And I look at Alfredo, who is going to present later. We need to work together for the same goal. The same goal that is to achieve to have a commercial project. The next one is standards. We have plenty of standards from oil and gas, already a lot of standards for bottom fix, and we have experienced people already from offshore floating from the new projects. Let's try, I'm aware that we are doing, but let's try to speed up and to have a good amount of standards to be used in the commercial scales project. Next one, as we were commenting before, another challenge is the construction timescales. We need to understand the logistical challenge. We are now speaking about port infrastructures. We are speaking about assembly processes. We need to speed up. We need to understand fabrication, also standardization, and we need to get it also working all together to work on that direction. We understand that we cannot pass from a project of 25, 30 megawatt to a 1 giga. We will need to go slow, steady, but go in the right direction. So we'll need likely to go and to step up to the next, that will be 200, 300 megawatt, 400, bigger scale, but not go farther than that until we see how all the logistics challenges are being solved. And then the last but not least that I wanted to highlight today in terms of challenge is the ocean criteria. We need also governments, regulation, to be aware of the timelines, to be aware of what is the current situation, that we need to take into account that the maturity of the technology is not the same than in bottom fix, that we need time. They are also bigger, higher cost. We need to consider that in the ocean criteria. We need to experience people work on it, and of course we need to have certain mitigation of those technical risks, and for that we need the cooperation and the support from everyone. I know that is a lot of information for this short presentation, but I just want to everyone take away the next 3 things, that we really need the successful of the first commercial scale project. We need to work together, everyone work together in the same direction. It's really important that developers, regulation, government, suppliers, developers, we work together to achieve that, to sail in the same direction. Thank you very much.
Thank you very much, Anna. So now we set a bit the stage with a developer point of view. Now let's move on to the O&M part. And let's move on with converters. We'll have Alfredo on stage. Do I need to present you, Alfredo? Alfredo is a group senior vice president and is head of renewables at Hitachi Energy. His role is to shape Hitachi Energy renewable strategy based on his deep understanding of the markets and the clients. Alfredo is also a member of management committee at Wind Europe, advocating for wind energy bringing value to environment, society, economy, and last but not least, to the grid. Alfredo, please.
Thank you, Maxine. Thank you, Anna, for your first presentation. And it's good to be back in the FOWT. This is where I start learning about floating offshore wind, and that's what motivated me to bring my company into this field quite a few years ago. So for those who are not familiar with Hitachi Energy, we are a high voltage equipment manufacturer. So we mean high voltage, we mean HVDC, STATCOMs, digital. We were part of the former of ABB, and today part of Hitachi Group since 2020. So for my presentation today, after the view of the developer, I'll bring you some hints of what we do in Hitachi Energy to get ready on floating substations. I will first address some of the challenges that will be a nice connection with what Anna presented. I will give you quite a good overview of the R&D program we are running for floating substations in the company. I'll tell you where we are today. I'll look at what's coming next, namely cost out and cost out strategies. And I will finish my interventions discussing about industrialization and lessons learned from fixed bottom offshore wind. So let's get started. Challenges, it's really kind of a warm-up because most of the things that I'm going to tell here are very well known by all of you in the audience. But at least allow me to set the stage. Going floating means that we'll face environmental conditions that are harsh. That's nothing new, that's common for bottom fixed. But we'll face this constant mechanical solicitation coming from waves, winds, currents. And all those mechanical solicitation are translated for the equipments that will stand on top of the substation. They will translate into vibration and tilting. And that's what we have to face. That's what we have to integrate in the design. We know about it because we face those solicitations where we transport our substation on sea from a yard to a destination point. But the difference this time is that those solicitations will be there for the 25, 30 years operation of the asset. So that's what makes floating substation special. This solicitation apply to high voltage equipment. We are entering then into a world where we look at the long-term performance and integrity of a critical asset, because that's what the substation is. Eventually is what is going to connect the megawatt, the gigawatt of generation to the grid through the substation. So we need to make sure that this asset is designed to perform during the whole lifetime, which brings us into a new area, which is the fatigue engineering. This is what is about taking all those mechanical solicitations into this long-term horizon. We're talking about fatigue, and that's where we need to excel. The third challenge we face is the technologies. We are focused right now on AC-connected substations, AC substations, and that's what we're working on. But we know that to tap the full potential of floating, we have to go deeper, further deeper in the sea, and the size of those wind farms will get bigger. And that calls for HVDC, which means we have to start developing now floating HVDC. And the challenge here is that the number of components we will have to prepare and design for this new mechanical environment is multiplied by the number of 4 to 5. So that tells about the level of complexity that we are facing. The next challenge I will mention is the floater design. We don't expect to have one standard floater design to work with. We don't expect either to see the same viability of floaters as we see for wind turbines, but we do expect that we have to face different design of floaters. The last point I will mention is standards. That was also referred by Anna. We don't have standards for high voltage equipment in this environment, and this is critical. We know by experience that if you start designing, constructing, commissioning without standard, is a very good recipe for big challenges. We had our part of it when we built our first HVDC converter station for Germany, where we faced many challenges during the executions, and I would say 90% of them were related to the fact that we didn't have a standard that could allow to align the OEM, the yard, and the investor. So that's the stage. So far, so good. Let's move on in our story, and let's talk a bit about this R&D program we are running in Hitachi Energy now for a few years. let me start with a kind of a foundational assumption and statement. Our program is floater agnostic for different reasons. The first one is that we as Hitachi Energy, we don't see ourselves engaged in any work in designing the floater or the mooring system. This is not our core discipline or core knowledge. Others do that much better than we can do ever. We have learned in this energy transition that if we want to grow at the speed and scale required, we need to focus in our core business and our core knowledge, and that's electrical equipments. So we want to be floater agnostics. We want to make sure that the equipments will be designed, can withstand the solicitation when they are built on any kind of floater. But that comes with another dimension. We also give the freedom to the developer to choose the floater and the yard they prefer, based on the location, local regulation, local content requirement, you name it. So for those reasons, we believe it's important at the foundation of our R&D program to stay floater agnostic. From there, the core of the activities we do is around product mechanical studies. So we want to study the design of our transformers, of our reactors, of our breakers, and of our control and protection panels. So these are the equipments we are looking at upside down to make sure that can withstand the lifetime solicitations. And how do we do that? Simulation. That's the first tool we use. We build the finite elements models for those equipments, and then we run different kinds of simulations, fatigue simulations, to see how those models are behaving during the lifetime and facing different cyclic loadings. We do ultimate limit simulations that bring those models to the harsher conditions and the more severe loadings they can face. And accidental limits simulations, also what if an accident happens, which means we go beyond any of the conditions that were part of the design criteria. So with this kind of set of mathematical tools, we are able to understand how the components are behaving, and we do those simulations from the component, the transformer, the switchgear, to the components that are part of those equipments, namely a tap changer, a bushing, or a breaker inside the breaker. So we go down to there to make sure that those components are also able to withstand all the solicitations. And once we have done those simulations at the component level, we go at the system level, and we do this FMEA analysis, which tell us what is the behavior of the whole system, what are the failure risk we do have in an overall system to be able to calculate the performance and the reliability. So that's what this R&D program is done, and then it's supported with validation tests. We bring the components and the products through the vibration and tilting test. We can also support and participate to a basin test where water basin test will be able to verify some of the assumptions we have taken in our simulation and mathematical tests. So this is really the core of what we are doing right now on our equipments. In parallel, we are actively engaged in the DNV GIP, the Joint Industry Program, which is, as you know, in its phase 2. And one of my colleagues is chairing, actually, this phase 2 of the program. And last but not least, we look for collaboration. It's a word that Anna used already and will use extensively, collaboration with yard and EPC and designer. Because eventually we need to check the assumptions we take in that are coming from the design of the floater, and we need to optimize the overall system, and I will come back into that. So with all this, where do we stand? Basically, when it comes to AC substations, we are ready. We have entered into the commercial phase. We are supporting developers who are in the early stage of their developments, and we are entering commercial negotiations for projects that are already at that stage of development. So that's what we've been able to do, and at this commercial stage each project and each design is project-specific for the specific conditions of the water we are working and for the specific floater we are working on. There is no standardization, it's project-specific, which means the work it requires, project by project, to develop the solution needed. For HVDC, as I said, the level of complexity is increased by a factor of 4 to 5, which increases exponentially the number of simulations and verifications we have to do. We are going thoroughly through the process, and we believe strongly that we'll be ready for when HVDC will be required. And HVDC will be required when the farms will be at the size it's required, and when the cables also will be ready, and the rest of the supply chain will be ready. But the program started already a few years ago, and we are making good progress on that one. So moving on, what is next? The name of the game, or in our industry, we are used to that, is LCOE reduction. We need to bring floating offshore wind to the level of competitiveness required to get its space in the energy mix. So some hints, some drivers we think will help us to get through the journey. The first one we know is scale. We've been through that, we are through that in bottom fixed, size of the wind farms, increased voltage of inter-array cables, of export cables. It all talks about size, but that's common to fixed bottom, and we'll enjoy this scale effect also in floating offshore wind, for sure. The second element you can think is about the equipment cost, the cost of this transformer, this breaker I mentioned at the beginning. Yes, it's true that through those verification and simulation we have done, we've learned how and where to reinforce those equipments. But the truth also is that those equipments are already designed in a quite robust manner. So the cost increase you have to get this mechanical robustness is not that big. So from that standpoint, that's not a huge cost driver. What is a cost driver, however, is the amount of engineering time and calculation time and verification time you need to bring those designs to construction and to the market. And that's for sure an area where we'll see cost reduction. The more experience we get, the more mature we are in this industry, the less we have to invest in those engineering works. So from an equipment cost, this is where the savings will come from. The next pocket for cost saving is the floater design. And it talks about industrialization. There's a lot that can be done there. Again, we've learned from different sectors, marine, wind, renewables. We learned that industrialization brings benefits, and there's a lot of benefits to be brought in the picture. The next one is combining the two, the equipment and the floater, because the dynamic behavior of the floater have an impact on the high voltage equipment. And you can come with some very absurd situation. I say, okay, I will reduce the cost of my floater to the maximum. Well, many will have something that shakes a lot. And if it shakes a lot, then you will have to over-design your equipment. And you come with non-reasonable CapEx and OpEx on the equipment side. So we can have this kind of intuition that floater design and equipment have to be optimized together. And it's not only an intuition, it's a reality. So that's where we think also the cost optimization will come, with this fine joint optimization between the equipment manufacturer and the floater designer. On top of that, we foresee other optimization opportunities. We can think about monitoring, the role that digital will play. It will help us to optimize design. Tailored operation and maintenance procedures, tailored design for CapEx and OpEx, not only for CapEx. And the whole potential from industry collaboration. So bringing the marine expertise with the mechanical expertise, with the electrical expertise together, this will bring us all benefits and synergies. And the last one that comes to mind is standardization. But let's reflect for a second on that one. We can think about standardization at the equipment level. I want to have my transformer, which is floating proof all conditions. That means all kinds of sea conditions, all kinds of grid code requirements. Maybe that's not very smart, because you may end up with a super big, super bulletproof equipment, but at an unaffordable cost. So equipment standardization, yes, but to a certain point. And then the overall design standardization, yes, it will be part of it. But let's not rush into it. Let's not define too strict standards from the beginning that keep us in a carcan, in a situation where we cannot move and there is no room for innovation. We need to keep room for innovation, to keep working on cost reduction and affordability. So that's where I'm saying standardization, yes, but at the right time. So probably more of a midterm kind of development, and taking standardization on the fleet approach. So some hits on where cost out can come out. And to conclude my presentation, what can we bring in this conversation from the experience we had on fixed bottom? A few things I would like to mention. First, we have learned together that early engagement pays off to de-risk project, to optimize design, to optimize performance. And this is called pre-FEED and FEED studies, something we learned from the oil and gas industry, and that has been heavily used in the last years. And that's going to play also a role on floating. Let's make it part of our journey. Business models. We learned that also in fixed bottom offshore wind. For us, it's very important. I said it at the beginning. We want, as Hitachi Energy, to stick to our core business. We want to develop the industry at speed and scale required. So we need to invest the dollars we have in what we do best, in the engineers that do what we do best, which is electrical engineering. So we are strongly advocating for a business model where we can stick to what we do well, the electrical system, and we can collaborate with EPCs and yards who take care of the mechanical side. So this has been applied in a number of projects, and we strongly believe this is a way also to reduce cost while keeping the risk under control with a proper interface management. Scale, again, comes here, and here I have to mention the 2 gigawatt TENET program for HVDC converters. So basically, they went to the market with 10 HVDC connections. Unthinkable. And this has been the game changer. So the game with that size of volume to the market, the volume was shared among the 3 main OEMs. And with this, we have now visibility to work on standardization, work on designs, and also to invest heavily in our factories and engineering capabilities. So we have to see how in this offshore wind market, in this floating market, we can bring this kind of volume thing. And I think this morning presentation, RTE, gave us some hints where the things can come. Yes, the TSOs have this power, this firepower to drive this kind of volumes. And we learn also how pre-engineering can work. In our world in Hitachi Energy, we call it grid expand. So grid expand is about a pre-engineered design for an offshore substation, modules for 400 megawatt to 2 gigawatt. That helps a lot in the early designs, early phases, where you have to talk with the developers on the preliminary designs, what could you look to look at the first investment cost. And that will help us also in the standardization journey. We need also to bring into the picture the security of supply. And I have to mention this also in this audience. We are in super cycle for energy. Offshore wind may go to these ups and downs, but offshore wind is only one part of the picture. We have all the renewable segment that is growing fast. We have all the T&D investment that are happening. We have data center, electrification, you name it. And this is calling on the T&D industry. So we are part of this conversation about availability of components. Long lead items are well known, and we have to integrate management of that also in floating offshore wind. And last but not least, to take your picture, Anna, we have to go through or work in the same direction. Collaboration will be key. So I've said it because of our business model, and we have repeated also because of the complexity of the sector. So thank you for your attention, and look happy to get your questions.
Thank you very much, Alfredo. Always have a pleasure to have you, your enthusiasm. I guess just the microphone don't enjoy your enthusiasm, but we enjoy it a lot. Now, we talked about converters. Let's go to a subject that personally I'm very enthusiastic on, dynamic cables, but I will not talk about it today. Michael will do that for me, or for us, from Technip FMC. He has 25 years of experience in subsea projects and tendering, primarily from major EPCI projects at Technip FMC in France and in Norway. And since 2021, he has transitioned to business development team, and he coordinates Technip FMC's new energy activities in France and in Norway, in CCS, in hydrogen, and of course in floating renewables. Michael, the floor is yours.
Thanks, Maxime. Okay, thanks for having me. So, good presentation. I recognize myself, that was correct. I start with a presentation today on cables, because I think we need to think a little bit about cables. We are looking a lot about the big items, and sometimes a bit less to what's subsea. So this presentation is going to be about the the challenges, the technical challenges that we meet when designing dynamic cables. And there is a good news about it, is that we've got quite a lot of experience from the oil and gas business that we can export to floating wind. So if we start on the first slide, I will start probably, oh yeah, it's me, okay. I was authorized to have one slide on the company. So for those who don't know the company, I will start by stating what we are not before saying what we are. So we are not Technip Energies. We are two different companies. We are called Technip FMC, and our specialty is the integrated EPCI. That means that there is a good part of the company that is on the oil and gas part, and that is delivering all the wellheads, injection wells, and Christmas trees, and so on, flow line on the seabed. On the renewable space, we are looking at three different pillars in new energy. The first one being the carbon injection subsea, so the wellheads and trees and flow lines transporting the CO2 and injecting into reservoir. The second pillar being the hydrogen, where we actually storing the hydrogen subsea for safety reasons, but also to stabilize the production of floating wind, for example, or any floating renewable. And the last one being the floating renewable. That's the topic of today, obviously. So on the floating renewable, Technip FMC has a big ambition, and this is to be the integrated EPCI contractor for the water column, i.e. everything that is subsea. So it's pretty easy to remember. So our mission is to supply the anchor, the moorings, and the cables, and to install them, EPCI. Within that part, we focus on the cable for today. The cables, just a reminder, we've got our own factory, so it's a pure EPCI, where on the mooring side we will be purchasing, just a detail. So why am I speaking about the cables today is that the dynamic cable are a special beast, because there is a trap there. Lots of cables have been installed in the past in fixed wind. Now we're talking dynamic, and there is a trap in thinking that it's going to be pretty similar. I have some bad news, it's not, and you've probably seen it on the pilot projects. The dynamic cables are really something different, and this presentation is going to focus on what is new, because it's fine, the dynamic cables for power, the industry, the oil and gas industry has a lot of experience with it, like 40 years experience with designing this complex umbilical that you got on the left-hand side, where you have different, you have power, you have signal, you have injection of chemical, and so on. So there's a lot of challenges, technical challenges linked to the dynamic part that has been resolved already and that are managed as per today. So that's the good part. We're not starting from scratch. When you compare to the right-hand side, which is a typical 66 kV dynamic cable, the first reaction is that it looks simpler, right? It is simpler. The cross-section is only these three cores. However, there are other challenges that are brought with that, and in particular is the fact that most of the floating wind fields are in very shallow water, and the shallower it is, the more dynamic it is. So these cables are going to be subjected to much higher dynamic load. But not only that, but they're also transporting a lot more power than the oil and gas is doing, and therefore there is a combination of heat and dynamic behavior. And finally, the last one, which is not to be underestimated, is the scale of it. When we start on a typical oil and gas field, we have maybe 1 to 10 umbilical to install, to produce and install. Here we are talking about another scale, we are talking 30, 50. So there is a key, and everyone has been talking about it today, of standardizing both our design, our processes, and also our product in a way, and our way of installing them. So that's the main, let's say, the high-level difference between the two. Now moving into a typical installation spread that most of you are aware of. So typically we've got the tensioner to hold the tension, we've got a chute, and we've got the buoyancies. attached to it. So every time we do something, every time we handle a cable, we transpool the cable to a reel, we install this cable, we hold the tensioner, we put on the chute and clamp the buoyancy. Every time we do that, we are applying loads on the product, right? It's obvious. We know those loads quite well from the oil and gas, again, because on the umbilical side, we've been doing that for years. So what's different? Again, if you look at the two cross sections here, it's quite obvious. The size of the conductor is much smaller, and therefore there are quite some conservatism in the insulation layer, among other things, that put the conductor in a safe place. The conductor on umbilicals is also quite surrounded by a full bundle, which makes the compression or the loading that we apply to it during handling and installation a bit more gentle. When you look at the right-hand side now, you've got the dynamic cables where it's fully mobilized under the compression of the tensioner, the clamp, or whatever you will attach to it, and therefore it's immediately in contact with the loading. So I'm not saying it's dangerous, I'm saying it needs to be properly designed and assessed. And the key here, if there is a message to the presentation, is that when designing these dynamic cables, we need to be fully aware of the failure modes. We need to analyze the failure modes and address them. Because these cables are so thick that they will generate heat, and the heat will generate premature aging of different sheaths and different material within the cable. So this premature aging needs to be taken into account in the design. You might have a cable that runs for several years without noticing that the aging is faster than planned, right? So that's what's illustrated here in terms of installation. Now moving into the in-place, once the cables are installed, you have a typical lazy S configuration like that in shallow water, where you got buoyancies, you got a tether clamp at the bottom. This configuration is to reduce the impact of the dynamics on the cable. It's pretty important because you might damage your cable if you have too much dynamic. So again, what can happen here is that just like when you're installing, there is different areas where there could be applied some cyclic bending, and this cyclic bending is combined with high temperature, right? And if for some reason you would kind of compress too much at any stage this white layer that you see, the insulation, then it will create higher stress into the whole system. It could create asymmetrical heating, and then in the end you start to heat the different layers of the bundle again. So you have the illustration here on the right-hand side. I won't say too much, but there is some electromagnetic effect here that could lead to having some current in the carcass structure of the bundle, and therefore having some heat generated and premature aging. Again, that was for the heat, but again, these dynamic cables are more dynamic than what we used to see in the umbilical business, right? So you could see it very easily at the top. You would have a high bending at the top at the floater. You would have as well some compression at the touchdown point. You would also have potential lateral buckling effect at the part of the cable that is laying on the seabed. All these effects could lead to overbending the dynamic cable. Again, those effects are well known on umbilicals, but when you talk about dynamic cables, it's amplified by the fact that the cable is hot and that the higher stress is higher. So you have more risk to damage your cable at a later stage, or to reduce the fatigue life, right? And then finally, and last but not least, pretty important, today there is not a unique code to design those cables and to qualify them. which is a bit annoying because we are talking about standardizing a product and making sure that they are all alike and all tested against the same regime. So there is a lack here of guidance. There are different guides, different codes that are addressing different kind of failure modes, but there is not a unique one addressing all modes. So it's just highlight that there is a gap here that needs to be filled in. So today, the cable suppliers are basically testing their cables in accordance with what they think is the right thing and trying to get the codes, the best code to fit in and having a third-party verification following that. So very important to note that there is a gap here. Why am I saying all this today? Because we've been talking about very big items here, and I'm just talking about cables. There is something about cables. That's the one on maybe I should have said that at the very beginning. There have been some studies done on those cables, and it shows that they don't count too much on the total cost of the development. We are maybe at 5–10%, but they represent 70 to 80% of the insurance claim. So what are we actually doing here? If we underestimate those cables, we might put the whole floating wind industry at risk. Because if we start having a lot of insurance claims, there will be a lack of belief in the floating wind, and in the end, we will struggle to get all these floating wind projects in shape. So all I'm saying is that we should not underestimate it. We should consider that as a serious challenge, and the good news is that it's a manageable challenge because there's a lot of experience coming from the oil and gas that we can export directly, and we can use those experience to have a better understanding of the failure mode and managing them in the future. So again, key is managing of the failure mode by having a system approach. We can't keep designing the cable for just being in place somewhere in water. We have to design them to be installable, to be so that we can handle them, and so that they work in operation for the design life that is allocated. That's what I had. Thank you.
Thank you very much, Michael. It was a great presentation, great illustration on dynamic cables. I think you show. I agree with all you said, and it was a great summary and great illustration of the challenge. Maybe so now it's time for the Q&A session. So first of all, thank you for respecting the 15 minutes. So we have time for some question. Maybe to trigger a bit as well the discussion with the assembly. I mean, after each of your presentation, do you think we're ready for commercial projects?
I will start. Yes, I think we are, but we need to keep in mind all the challenges that all of us we have commented. Challenge in terms of the technology, in terms of the standards, in terms of the logistical challenges. So for that, and I come back again to the same topic, we need to be working together in the same direction, timescales, target. Not only us, that we represent supply chain developers, regulation, government, environmental, permitting, everyone needs to be on board on this, because the first project needs to be a success, and we need to have that in mind.
So to build on what you said, a success, of course, and I would say, let's put us in the condition that is a success. So to answer your question, yes, we're ready for commercial. I said it in my presentation, but let's make sure we start with the right step, which means also, let's not rush on the competitiveness story of floating. We'll get there. I mean, the industry, fixed bottom has shown that we had dramatic cost reduction. We can make it. So, but let's start with let's give us some room for developing what we have to develop. We've said it. We know what we have to do. We just need time. We need time to learn, to get mature. So, but let's have the right steps from an auction perspective, which is probably a message to the institutions and to those who are designing the auctions.
Well, you said it already, so I don't know what I have to add, but coming back to the presentation, we need to understand properly the risk of what we're doing. And it's not only the technical risk, it's the risk of interface, it's the all kind of risk, because I fully agree, it needs to be a success from the start. If we get the wrong signal, that's going to be even more challenging to get it done. So that's why the pilot projects are key. I'm very pleased to see that there are so many pilot projects. There are other pilot projects as well ongoing, including 15 megawatt turbines. And there are, I would say, it's the next step of importance, because that allows us to de-risk the projects. And that's a major point when we're talking about investors into the project, right?
Perfect. So early collaboration, engineering, and that everybody takes that into account. Good. I cannot see very much the room, but if there is any question, we will be happy to take them. You can raise your hand and introduce yourself, and we'll take the questions. Yes.
Thank you for a good presentation. My name is Anthony from the University of Maine. Just had a question about the dynamic cables. Great presentation from Mikael from Technip. What about the possible floating substations and the even higher voltage cables that might be required for the export? Are you looking at that? Can you comment on maybe those types of cables, dynamic cables? Thank you.
I was not planning to talk today, but I can answer. Yes, so Mikael rightly covered the array part. Clearly, the industry as well is working on the export cable side, and as similarly to what Alfredo said, we are ready now for AC, and we are also starting to work towards HVDC dynamic cables. So for the HVAC, we are building on what has been done in the oil and gas. It has been already several projects of electrification from shore in the oil and gas business, up to 145 kV. And some are already operational. Some will be built in the coming years. And 245 kV has been already qualified by at least one player in the industry. So in terms of HVAC, I would say the innovation and the research and development is ongoing, and I would say it's almost finished and completed, and we are ready, and we have already proposed it to commercial tenders for commercial floating wind farms. And then the next step would be HVDC with, I would say, similar challenges of what we see and similar kind of technical blocks that we need to go over to go from static HVDC to static HVDC cables to HVDC dynamic cables.
Question for Hitachi. I know that in some Italian floating wind projects, the developers are considering subsea substation, maintenance-free subsea substation. It seems very ambitious to me in order to avoid the maybe technological difficulty of a dynamic floating cable. What is your point of view as a technology provider on that option? Does that seem viable to you in terms of operation, maintenance, reliability, and everything?
So I can answer from the experience we have with subsea. So we are manufacturing, delivering, and operating subsea transformers for the oil and gas industry. So that tells it's feasible, so we know how it works. And what's the technology gap? Because I guess that's what we are talking, while we're talking about much larger equipments and much higher voltages. So there are companies that are working on that. As you said, in Italy, there is a project that did consider that as an option. I think that that's part of the development we have. When we think about what's the future of substation, what are the routes to market, that's why I see that there are many options, starting first having no substations. Second, in the floating part, having a fixed bottom substation with large jackets, go for a floating substation, or go for a subsea. So what's going to be the winning solution? The jury is out. And for us, we work in all the options, including subsea, because we think it has its merits, but we should not say, okay, we've done it for oil and gas, then we can just scale it up a little bit, and then we have now a large scale. So we're happy to see companies who are starting working on that, and we are supporting them.
No more question? Because we cannot see very much now. No? Thank you very much.
Thank you.
Thank you for respecting the time to give us at least a bit of question. Thank you for the preparation and the great presentation. Again, maybe a round of applause for the three presenters.
So thank you, Maxime. Thank you to the rest of the presenters today. It was surely an interesting learning experience on how these dynamic systems for cables, for floating offshore substations will come to life.